And welcome to Conceptual Physics at Delaware Tech, Chapter 9, Gravity. So in this unit, we're going to talk about the Newtonian synthesis. This refers to the application of all three of Newton's laws of motion and how they apply not just to things on Earth and things on other planets or moons, but also within the entire universe. We'll talk about the formula that he generated called the universal law of gravitation. And we'll talk about parts of that formula that involve a constant called the universal gravitational constant. We'll talk about how the force of gravity is related to distance, and this relationship is referred to as the inverse square law. We'll also talk about weight and weightlessness, really apparent weight, how much weight you feel you're experiencing under certain conditions, including free fall, when you're falling from the sky or maybe orbiting in a space station. We'll talk about how the gravitational force between the Earth and the Moon, the Earth and the Sun to a lesser extent, create ocean tides. And then we'll talk a little bit about how our modern view of gravity is completely different from our Newtonian view of gravity. Einstein revolutionized the thought of gravity. Instead of thinking of it as direct forces, the way Newton has led us to think about it, which is fine under most conditions. Einstein proposed that gravity is really a distortion of the space-time continuum, for the better word for it, but of space-time, and how all masses distort this space-time. And then we'll talk about some distortions of space-time called black holes and wormholes. And then we'll briefly talk about how this applies to the field of universal gravitation. So, Newtonian synthesis. Newton wasn't the first one to discover gravity. People knew there was something pulling objects down long before. But what Newton realized is that this gravity is universal. In other words, while he's looking at an apple falling from a tree, he realizes that the same force that's pulling the apple down or pulling people down when they fall, or any object that drops, or something that's shot up in the air and it comes down, he realized that force was the same force that was responsible for holding moons in gravitational pull to the planets, or planets being held by stars, as specifically our planet with the sun. So he realized these are really different manifestations of the exact same process, the exact same gravitational force. So this synthesis refers to how he was able to apply all of his laws, not just to everyday events on Earth, but to the events of the heavenly bodies, the sun, the planets, the moons, even the other stars in the sky. So in Aristotle's time, so this is way earlier than Newton. Newton was in the late 1600s, early 1700s. Aristotle was a few hundred years BC. So Aristotle believed the motion of the planets and the stars was quote-unquote natural. In other words, it wasn't governed by exactly the same laws as objects on Earth. Newton realized that the force directed on the sun must act on the planets. So in Newton's time, they realized the sun was the center of the solar system, not Earth, and realized that there must be some force keeping the planets held to the sun in orbit. So he noticed that this force that was exerted on an apple or everyday objects that he saw on Earth must be the same force that is involved in the heavenly bodies and their gravitational forces. So this Newtonian synthesis applies to both celestial objects, celestial meaning in the sky, in the heavens, and terrestrial, meaning terra, Earth. That's happening right here. And so this is why we say his laws are universal in scope. They cover everything, both the heavens and the Earth. So the law of universal gravitation, this basically states that everything with mass pulls on everything else. In other words, everything with mass has gravity. Everything, even something as small as a proton, or bigger like us, or planets or moons or stars, we all have gravity. Obviously, there's different amounts of it depending on the amount of mass you have. And what was realized was that this gravity, this attraction that every body, meaning any planetary body, human body, particle body, any object with mass, the force is directly proportional to any mass that's involved with gravity towards any other mass. And if there are two bodies that are attracting one another, the gravitational force is proportional to both of those masses, or we would say that it's proportional to the product of the masses, mass 1 times mass 2. So if you increase mass 1, you'll increase gravity by the same amount. If you increase mass 2, you'll increase gravity by the same amount, the force of gravity. If you increase both of the masses, then you have two increases in the force of gravity. And what was also realized is that the force of gravity is inversely proportional to the square of the distance separating these two bodies. And when we say distance, we don't mean the distance from their surfaces, like the surface of the Earth to the surface of the moon. We mean the center of the Earth to the center of the moon, or the center of our body to the center of the Earth. We don't usually do the center of our body because we're so small compared to the Earth. But when you do these calculations with large objects, you are always concerned with the center of mass of that body, or the center of gravity of that body. That's where you can think of the mass being concentrated. It's not concentrated, but mathematically it can be treated as if it's a single point in space at the center of whatever object you're looking at. So you look at the centers of the objects and the distance between them. And what was found was that gravity is proportional to the square of that distance. It's inversely proportional. So if we double the distance, we will double the drop in force. In other words, it's squared. So if we were to triple the distance, that means we're changing our distance threefold increased. We will decrease our gravity threefold times threefold, or ninefold decrease. If you bring the distance in closer, the force of gravity will go up dramatically with the square of that change in distance. So that's a square term, and you're going to see this inverse square rule several times. We're going to see it with gravity. We're going to see it with electric force between positive and negative charges, or positive and positive charges with repulsion. We'll also see it with magnetic fields. Most fields, when you separate them, they respond by being weaker with the square of the distance that you're separating these objects. So if you put these things together, we know the force of gravity is proportional to the mass of the first thing. We know it's proportional to the mass of the second thing. So both of those will be in the numerator. We also know it's inversely proportional to the square of the distance. That goes in the denominator. So now we know it's proportional to the whole thing. Force of gravity is proportional to mass 1 times mass 2 divided by the distance squared. Now, so what this means, like I've already explained some examples, the greater the masses M1 and M2, the greater the force between them. The greater the distance of separation, the weaker force of gravitation, but it's much weaker because it's a square of the distance that it's affected. So Newton's most celebrated synthesis, the Newtonian synthesis, the combination of ideas to form a theory or system, that's what we mean by synthesis, was and is of A, earthly and heavenly laws, B, weight on earth and weightlessness in outer space, C, masses and distances, D, the paths of tossed rocks and the paths of satellites. Well, the best answer is A, earthly and heavenly laws. It's everything, which encompasses most of B, C, and D as well. So his laws were proved to be universal. In other words, they explained all types of motion, what we saw on Earth, what we saw in the heavens throughout the universe. Okay, and the synthesis provided hope that there would be other natural phenomena that followed universal laws. In other words, it was hoped that all of the great laws governing how the universe worked would work just as well on Earth as they did in space. And this was part of the concept that led to the Age of Enlightenment in that period of time. Gravity is the weakest of the four known fundamental forces. Now, we don't talk about two of these forces that much in this course, the strong nuclear force and the weak nuclear force. The strong nuclear force is involved in keeping protons and neutrons together within the nucleus, and the weak nuclear force is involved in certain types of radioactive decay. We do talk about the electromagnetic force in chapter 22 and 23 and 24, and we talk about gravity here. So gravity is by far the weakest of the four known fundamental forces. but it is the most important force when we're looking at large distances between objects, especially the large distances we see between moons and planets, between planets and stars, between stars and stars, between galaxies and other galaxies. Gravitational force is one of the biggest, is the biggest of the four fundamental forces in those instances, and it's by far the most important. So if we take the proportionalities that we already looked at earlier, where we see that gravity, the force of gravity is proportional to the mass 1, it's proportional to mass 2, and it's inversely proportional to the distance between their centers squared, we have everything in the formula except a constant, so that we turn what's proportional into what's equal. That constant just fixes the proportionality so it's exactly equal. So we use this constant that was calculated, and it turns out this constant is given a name, the universal gravitational constant, and this is good for all gravitation everywhere in the universe. So this constant is 6.67 times 10 to the minus 11, so it's a very tiny number, Newton meter squared per kilogram squared. So really, really small number, but it makes the left side of the equation, the force, exactly equal the right side of the equation, that mass times mass divided by distance squared, with an extra constant in there to make it all equal. And once this value was known, the mass of the Earth can be calculated, because what you might remember already, and you may be thinking, hey, wait a minute, we learned that the force of gravity is m times g. This doesn't look anything like m times little g. Well, it turns out that part of the equation is the little g. When you multiply the big G times the mass of the Earth divided by the distance from the center of the Earth to you, in other words, the radius of the Earth, you get about 10 meters per second squared. That is the G that we calculate. And if you put in different planets in here and different radiuses of that planet, you can get different gravitational constants, gravitational accelerations for different planets. You could get it for the, or moons. You get it for the moon, you would get about 1/6 of the value of G that we have, about 1.7 meters per second squared. If you put in Jupiter's size and diameter, you would get a number that's about 27 times bigger than ours. So you can use the same big G gravitational constant to calculate the little g of any heavenly body. This is a question that confused me a bit, but we're going to go through it anyway. Don't feel bad if it's not clear to you. The universal gravitational constant, capital G, which links force to both mass and to distance squared in the inverse proportionality, of course, is similar to the familiar constant A, pi, B, little g, C, acceleration due to gravity, D, speed of uniform motion. Well, if you look at B and C, those are the same thing. Little g is the acceleration due to gravity. That is our 10 meters per second squared that we're familiar with already. So it's weird that their two answers are the same, and that would make you think that's not the right answer, because it can't be both of those answers. And in fact, the answer is A, pi. Now, why in the world is A, pi the right answer? Okay, well, the author reasons that pi is the constant that fixes some well-known proportionality relationship. In other words, the ancients knew that the circumference was directly proportional to the diameter of a circle. The circumference of a circle, how the length around a circle is proportional to how wide the circle is. Well, it turns out the constant that makes that proportionality and equality is pi. The circumference is exactly equal to pi times the distance. In the same way that Newton's relationship of the force of gravity is proportional to m1 times m2 divided by the distance between the objects squared, that's the proportionality. By putting in a constant, you change a proportionality into a perfect equality. And I know that's a stretch, and don't worry if you don't get it. It's not something I would test you on directly. So this is just something the author wanted you to see. All right. So gravity and distance, the inverse square law. Now this is really important to understand, and it will come up, as I said before, in a few times. You'll get it with electrostatics. You'll get it briefly with magnetics. All right. So it relates the intensity of an effect, the force of gravity, the force of electric force, the force from magnetism, to the inverse square of the distance. That means if you look at the distance and you increase the distance by some folds, by some factor, you will decrease the intensity of the force or the effect by the same factor squared. So it'll be even more pronounced in the force that you're looking at. So, for example, for increases in distance, there are decreases in force by the square in the increase in the distance. What does that mean? If I triple the distance, I will decrease the force of gravity by 3 times threefold. In other words, I increase the distance threefold, I will decrease the force ninefold. If I increase the distance tenfold, I will decrease the force by 10 squared, 100-fold. If I shorten the distance by half, I will double the force. So cutting it in two means I'm decreasing it twofold. I'm going to increase the force 2 times twofold, or fourfold. So at even greater distances, force will approach zero, but it never becomes zero. What does that mean? That means gravity goes forever. No matter how big or small the object is, no matter how much mass it is, no matter how much distance, technically there is some gravity. It might be so small that we will never be able to detect it. We will never be able to measure it. But in theory, gravity, the field of gravity, the force of gravity goes forever. It just becomes weaker and weaker as with the distance squared. And this is true of gravitational force, of electric force, magnetic force. Technically, it's true of sound intensity, but in practice, sound intensity, eventually it just becomes heat energy that moves the air. Light intensity, even spray paint thickness decreases with the square of the distance. And so we'll talk about that. And so here's kind of an analogy. You're looking at a spray can. Think of the spray can as your source of gravity, and it's spraying out paint, and your paint that's sprayed out, you can think of it as the force from gravity being spread out from the object. Well, it turns out as you increase the distance, you will greatly decrease the force. And in terms of the analogy with paint, if you spray a further distance, that same amount of paint is spread in area, which is a two-dimensional surface, as opposed to the distance, which is a one-dimensional length. So what does that mean? Well, that means, let's say these units of distance, it says units of distance, let's just call them meters for now. You can see that if you look at 1 meter distance, you see the paint will spray a square of 1 meter by 1 meter, a 1 meter square area. So that's at 1 meter distance. But if we double our distance to 2 meters, the square will increase by the square of the change in distance. What does that mean? That means we went from 1 meter to 2 meters. The new area that the can is spraying is 2 meters by 2 meters, or 4 meters squared. And what that means is you have less paint to fill that 4 meters than you did with the earlier 1 meter, and therefore the thickness of the paint will get thinner by a fourth as you go back. If you go back 3 meters, it's 3 by 3 meters, so the paint thickness will go down to 1/9 of what you saw at 1 meter. So it's always going down by the square of the distance. And so you can do this analogy with paint, and this actually appears in your problem set. But this works with any field strength that is moving back as an area where they're feeling a field strength at a certain distance, and then looking at areas even further back where they're feeling the field strength that's weakened at a bigger distance because it's covering much more area. So this is the concept of the inverse square law. And here it is mathematically, graphically. Now, this graph isn't really complete because we're starting on the surface of the Earth. We're not starting at the center of the mass of the Earth. You can't start in the center. We will talk about that theoretically in a moment. But if you start at the center of the Earth, we're already 1 radius away from the center of the Earth when we're standing on the Earth. Oddly enough, they put the starting point on the surface of the Earth in the middle of the Indian Ocean, but I didn't make this drawing. So if you have an apple that's sitting there on the Indian Ocean, let's say, right on the surface of the Earth, it will feel a certain gravitational force. But if you move it one more radius away, one more distance from the center of the Earth than it was, in other words, we're doubling the distance it was to the center of the Earth, that's at 2D on this graph, you see the force of gravity goes down dramatically. It's precipitous drop, and that is because it is related to the square of the distance, not just the distance. If it was related to just the distance, we would see it go down as a line. But because it's with the distance squared, we see it go down very steeply. And by the time you're at 3 distances from the center of the Earth, 3 radiuses from the center of the Earth, 3 radii, if you say it as the Latins do, you're down to an even lower force. It's related to the distance squared as an inverse function. It's 1 over the distance squared. You don't have to remember the 1 over. Just remember, if you're increasing the distance, you're decreasing the gravity by squared of whatever you did to the distance, and vice versa. Okay, they're inversely related, but to the square of the distance. All right, so here are a couple questions to test your understanding of it. The force of gravity between 2 planets depends on their A, masses and distances apart, B, planetary atmospheres, C, rotational motions, D, all of the above. Well, remember the formula. The formula says force of gravity equals some constant, big G, times the mass of the first object, the mass of the second object, they're multiplied together, and divided by the distance between the object's centers. So it's only dependent on the mass and the distance. Rotation and atmospheres are completely irrelevant, have nothing to do with gravity. All you care about is where the mass is centered and how big that distance is between those centers. If the mass of one planet is somehow doubled, the force of gravity between it and the neighboring planet, A, doubles, B, quadruples, C, is reduced to half, D is reduced to 1/4. All right, well, we know that the force is directly proportional to each of the masses separately. So if we double the mass, we're going to double the force. And so it's a direct proportionality. Now, if you want to do the math on this, you don't have to. The second comment in the explanation just shows you how to think about it mathematically. You could just shove in 2m1 instead of m1 into your force formula. And then when you're done, you pull the number out to the side, and you can see that all it is twice the original force, the original G times m1 times m2 over d squared. So now you know that by doubling the mass, you double the force. And you could do this with any proportionality: inverse, regular proportional, direct proportional, inverse proportional, squared, cubed, whatever, by sticking in a number and seeing once that number is put in the formula, how, and when you pull the number back out of the formula, you can see how it affects the whole formula. In this case, it's just 2 times the original force. All right, if the masses of 2 planets are each doubled somehow, the force of gravity between them would be A, double, B, quadruple, C, reduced to half, D, reduced to 1/4. We know that the force of gravity is proportional to mass 1 times mass 2. In other words, it's proportional mass 1, but it is also proportional mass 2. Whatever you do to each of those, you will do to the force. If we double the first mass, we'll double the force. If we double the second mass, we'll double the force again. 2 times 2. And therefore, we will quadruple the force. It's proportional to each mass. And if you stick in 2m1 and 2m2 in your formula, you could pull the 4 out when you're done and see that you have 4 times your original formula, and that tells you it's 4 times the old mass. That's the mathematical way, but it's much easier to think of it in terms of simple proportionality and inverse proportionality when you're looking at the distance. So weight. Let's talk about weight and weightlessness. But now we're going to talk about not your true weight. This is more your apparent weight, the weight that you feel, the weight you actually feel that you are exerting on the surface of whatever you're standing on or whatever the object is sitting on. So this turns out to be the weight. The weight that you feel is actually the weight of the supporting force that's pushing up against you. That's what you're feeling. When you feel your own weight, you are also feeling the force of the ground or the bathroom scale or whatever you're standing on pushing up against you, that equal and opposite support force, the normal force that we talk about, N. So when you weigh yourself, you're really measuring N, the support force, the normal force. We just interpret this as the weight of our body that we feel on Earth. So for example, if you're in a completely stopped elevator or you're in an elevator that's just moving at a constant up or down speed, in other words, no acceleration. Remember, physicists really don't care whether an object is dead stopped or moving at a constant velocity, a constant speed, and a constant direction. To a physicist, those are more or less the same situation. They're only different by who's watching you. Are you watching from the inside of the elevator or somebody watching from the outside? And it's just a continuous movement. So in those cases, there is no net acceleration. So the only forces involved are your weight, the force of gravity of you down, mg, and the supporting force from the floor of the elevator or the scale that you're standing on in the elevator. Okay? And in this case, because there's no net acceleration, those two forces are exactly equal to each other, just opposite in direction. Otherwise, you would go through the floor of the elevator if you weighed more than your support force, or you would float above the elevator floor if your weight was less than the support force. But let's look at some situations where the elevator is accelerating, either upwards or downwards. Let's say it's accelerating downward. You're in a tall building. You're at the top of the building. You step on the elevator. It's not moving at all, and it has to start moving. Well, that moment when it's changing speed, going down, it's accelerating downward for that moment. In other words, the floor kind of drops out from under you. And in that moment, you feel less support from the floor. And as a result, you feel an apparent weight that's less than your normal weight, your normal m times g, your F sub g, your force of gravity, your W. Okay, you feel less than that because the floor, the support force from the floor is less as it's going down out from under you. Likewise, if you're in the bottom of a building and you start the elevator to go up, for that moment in time when the elevator starts moving, it has to accelerate upward, and you feel the floor just push up against you, so you feel extra heavy in that moment of time. That is the extra support force of the force from the floor being greater than your normal weight, your normal F sub g going down. And as a result, you feel heavier. So here, different examples that we just talked about. We just talked about the first three of these. Normal weight when the elevator stopped or just moving at a constant speed. You feel greater weight when the elevator is accelerating up, not just moving up constantly. It has to be accelerating up, increasing speed. You feel less weight when it's dropping down with acceleration, coming down, because there's less force of the floor pushing up against your feet. And if somebody snapped the cable on the elevator, you would fall. You and the elevator would be falling with the acceleration due to gravity. You'd be falling with g, but now there's zero normal force. There's no support force from the floor. It's not pushing you up at all. You're both falling down at the same time. You don't feel the floor at all, so you feel weightless for that time. You have weight. You just feel weightless because there's zero support force underneath you. So weightlessness is really when we experience no support force. In other words, where the normal force N is zero. We also call that free fall. We've talked about this before. Free fall, we're not going to talk about air resistance here. When you're just falling, that is free fall, and that is when there's nothing holding you up. So your acceleration is completely due to the acceleration due to gravity, g, and therefore the only force exerted on you is the one down from your weight, mg. There is no counter force from the support force. So astronauts in orbit feel this as well. A lot of people have this misconception that people on the space station that are floating around in the space station are weightless because there's no gravity. There is gravity there. In fact, if you do the calculations, they're not that far away from Earth. Their gravity, at that point, their g force, our g is our g acceleration is 10 meters per second squared. Theirs is about 9 meters per second squared. It's only a little bit smaller than ours. They weigh almost as much as we do, but they're in free fall because the space station that's going around the Earth is continuously falling, but it's falling at a rate, but it's also traveling horizontally. So it's falling into the Earth. It's also moving out of the way of the Earth. And what this ends up doing is just making it orbit the Earth all the way around. But when an object is orbiting the Earth, like a satellite or the space station, what it's really doing is constantly falling to the Earth, but also constantly missing the Earth because it's traveling so fast laterally, tangentially, that we learned in the last unit for rotational motion. So it's actually missing the Earth as it's falling, but it's always missing the Earth and it's always falling. So when people are on a space station, they are actually experiencing the feeling of falling the entire time they're on the space station. And this is why a lot of people have trouble with their stomachs and their heads when they're on there for long periods of time. Imagine feeling that feeling of jumping off a building for days, never landing, and that's what they feel. And skydivers feel the same thing for several seconds, more than several seconds, as they're jumping up until the point where they open up their parachute, and then they have the support force of the air resistance pushing them up. But it's not a true support force. It's really the frictional force of the air. All right, so when an elevator accelerates upward, we've already talked about this, your weight reading on a scale is A, greater, B, less, C, 0, D, your normal weight. Okay, so you're accelerating upward. What's happening? The floor is pushing up against you before your body realizes it, and you feel this increased support force under you, this increased N. Your weight is, your force of gravity is still exactly the same, but now for that moment in time of that acceleration, your normal force is greater than your weight, and you feel heavier as a result. And therefore you'll see a greater reading on the scale. And that's because the support force pressing you is greater in that moment of time when the elevator lurches upward. Now, if you want to know the math, you don't need to know the math. The way to think about this is the normal force is, there are only two forces acting on you. Your weight pulling down, that's F sub G, and the normal force, the floor pushing up against you. And the difference of those forces produces a net force, which is the acceleration, which creates the acceleration of the elevator upward. So you have this net force that is really N, the support force pointing up, minus the gravity, your force of gravity pointing down. And the difference is how you really are accelerating times your mass, the net force up. But in this case, what we're interested in is not the net force up. We know the elevator is accelerating up. What we want is the N, the support force, because that's what we think is our weight. That's what we feel in our body is how much we weigh. And in this case, you can see that just by rearranging the formula, because the normal force is greater than the gravitational force, normal force will be equal to the gravitational force plus that extra force because the elevator is accelerating up. And in other words, the normal force is greater than the force of just gravity alone. It has that extra ma term. And this is why you feel this extra weight. There's this extra term added to your weight that you think you feel because the support force has to be greater. The opposite situation, when the elevator accelerates downward, your weight reading on the scale is greater, less, 0, normal weight. Well, by now I think you figured out it's going to be less for exactly the opposite reason. The supporting force of the floor on you is less. It's dropping out from under you in that moment of time. And if you do the math on this, you have a force of gravity down, but you have a small normal force, a small support force up because it's dropping underneath you. It's not pushing up against your feet as much. And as a result, the force of gravity is greater than the normal force. And if you rearrange the equation to get the normal force, you see the normal force is the force of gravity minus your downward acceleration times your mass. That's your net force. And that just means that the normal force is less than just gravity alone because you're subtracting out extra amounts from the FG, from your weight. And that just means because the floor is dropping out, you feel less support force, and therefore you will weigh less on a scale sitting in the elevator. Now, would you still appear to weigh less in the elevator that's moving downward at a constant velocity? What a constant velocity, look at the formula that's underneath where it says beyond the scope. F sub g minus n equals ma. Well, a in that case, in constant velocity, a, acceleration, is 0. So that means that fg minus n equals 0. That means they're exactly equal to each other. The force of gravity, your actual weight, equals the normal force, the force of the floor, and therefore you will feel exactly the same weight. When the elevator cable breaks, the elevator falls freely, so your weight reading is greater, less, 0, normal weight. Well, in this case, it's 0. You have 0 support force. Remember, what the scale is reading is the force of it pressing with its springs up against your feet. If you're both dropping, that scale isn't pressing against your feet at all. There is 0 normal force, 0 support force from the floor, from the bathroom scale that's in the elevator. And therefore, you will feel absolutely 0 weight in that case, and this is just, there's no normal force here. The way you fall is the acceleration of gravity, which is due to your weight, m times g. So this is just saying that the force between the two is going to be equal in that case. When you have no support force at all, you feel like you're in free fall. All right. If you weigh yourself in an elevator, you'll appear to weigh more when the elevator does what? Well, we've been talking about this. Moves upward at a constant speed, moves downward at a constant speed, accelerates upward, all of the above. You weigh more. When do you weigh more? You weigh more when your support force is bigger. That happens when you're accelerating upward. It'll never happen when you're moving constant, either up, down, side to side. That has no effect. It's when you're increasing the support force upward. So moving it upward in a constant speed has no effect, or if you're just at rest, no effect. But you accelerate upward, that will increase your apparent weight. If you accelerate downward, it will decrease your apparent weight. So upward will increase, downward will decrease. Okay, so totally new topic, tides, ocean tides. Where do they come from? What are they? Well, tides are the differences between the levels of the ocean. Sometimes you'll see this even in rivers. On a rare occasion, you'll see it in lakes that are connected to rivers that are connected to oceans. But you see it in oceans, you see it in the bays of oceans, where the level of the water will change throughout the day. And these are called tides. Tides actually comes from an ancient word, tide, which means time, because these things happen with a certain regularity in time. And it turns out that you get a high tide, then a low tide, then a high tide and a low tide every day. 2 high tides, 2 low tides every day, almost every day. They're a little bit longer than a day because each of these tides, each of these 4 tides, takes about 6 hours and roughly 13 minutes, depending on what part of the world you're in. So it's slightly more than 24-hour cycle to get 4 tides, but it's roughly that. So if you look at tide tables, you'll see 2 high tides and 2 low tides for most days. And so what is the reason for this changing in the water level? Well, turns out gravity is the reason for this. Gravitational tides are caused by the gravitational attraction of the Earth and the moons. Mostly the moon, but also the sun to a somewhat lesser extent. And Newton figured this out as early as 1687. And the reason for this is when you have an object that's pulling on the Earth, it will stretch the Earth. It has differential pull on the part of the Earth that's facing the moon. It's a little stronger there than it is on the part that's facing the opposite side of the moon, and will actually stretch the Earth into almost an oval type shape. Well, most of the Earth is made with solid material, so that doesn't really move much, but the oceans are very fluid by definition, and they will actually respond to the gravity much more. And as a result, you end up with this permanent bulge in the Earth's oceans that is always bulging on the front side towards the moon and the back side away from the moon. It's just kind of stretched over. So you end up with this oval of water that the Earth is actually spinning inside of. And because the bulges are on the opposite sides, you get high tides every 12 hours. You get a high tide when it's facing the moon, and you get a high tide when it's facing exactly opposite the moon. And in between are your two low tides. So the tides we think of the tides as coming in and out because our frame of reference is wherever we're living, wherever we're looking at the water. But the fact is the Earth, the water is actually staying there. I mean, to a certain extent, it's moving, obviously. But the bulge is always there, and the Earth is just rotating into different parts of the bulge every day. So it rotates into the right side of the bulge, and then it rotates into the left side of the bulge. That's the second high tide. And it just keeps doing this, rotating in and out. So tides are not really coming in and out. We're actually rotating into the bulge of the high tide every 12 hours. So it goes up, goes down, goes up, goes down every day. Two of each. Now, there are different kinds of tides and with different strengths. And the strongest tides are tides called the spring tides. Now, I told you that the moon is the primary cause of these tides, but the sun can contribute to them because the sun is much farther away, but it also has much, much more mass. So even though the distance is much further, it's 400 times further than the moon is, it's also much bigger with a lot of mass to it, so its gravitational pull is pretty significant. So when the moon and the sun are lined up with the Earth in one line, and that can happen either in the new moon when the moon is between us and the sun, or the full moon when the moon is behind us, so we're between the moon and the sun. Either one will stretch out the bulge of the oceans. And if you have the sun in the same line, the sun will make the bulges even bigger, and that makes the high tides even bigger than normal in a regular tide. Now, when you have first quarter and third quarter, that is when the moon is in an angle that's 90 degrees relative to the angle to the line we form with the Earth and the sun. And that can happen either when it's in the first quarter or in the third quarter. Those are your half moons, basically. When you have half moons, the moon and the Earth and the sun are not in a line. They're actually in a right angle. And therefore, this bulge that the moon is trying to make, in this bottom drawing, it's making it vertically. That bulge is making it vertically up and down. The sun is trying to make the bulge this way, so it actually flattens out the bulge because it's trying to squeeze the bulge in a different way. And as a result, the tides are much lower in these. And these are called neap tides. They're the less pronounced tides. The high tides are not nearly as high as you would find in spring tides. The spring tides being the new moon and the full moon tides. So, and neap comes from an old English word that means narrow or small or shortening. So those are the lesser tides. All right, gravitational fields. So there are different ways to think about gravitational fields. Newton thought about gravity in terms of forces, not as much about fields. And we have this interaction between the Earth and the moon, or any two heavenly bodies that are acting at a distance. They're not touching each other. How are they interacting with one another? Well, there are lots of ways to think about this, but one way is to think in terms of gravitational fields. So these are force fields that radiate from the Earth, that radiate from any body that has mass. And so the Earth has its gravitational field that gets weaker and weaker as it goes further out. The moon has its gravitational field that gets weaker and weaker as it goes out. And the Earth will interact with the moon's gravitational field, but the moon will interact with the Earth's gravitational field. And we know from Newton's third law that the force that the Earth exerts on the moon is exactly equal to the force that the moon exerts on the Earth. Just like the force that the Earth exerts on us is exactly the force we exert on the Earth. We don't see that force on the Earth because the Earth's so big, it doesn't accelerate very much like we do when we're falling. So gravitational field, in terms of what Einstein felt, was an alteration of space. It actually changes the fabric of space. Really, because we now think of space as a combination of the three dimensions of space and the one dimension of time, we put them all together and we call it the four-dimensional space-time. So that's the fabric of space-time. And it's now believed that big masses distort this fabric. I know that's a weird concept to conceive in your head because nobody can think in 4 dimensions or multi dimensions beyond 3. It's very difficult. So this is an unusual concept to really grasp viscerally in your head here. But you can think of it in terms of there's this force field from every object that has mass. And you're warping that space-time whenever there's mass present, and that affects the other masses near it. And in fact, it doesn't just affect the gravity of the forces pulling objects to it, it actually distorts time. High amounts of gravity will actually slow down time for you. And you might have seen the movie Interstellar. They didn't get everything right there, but the idea was they were in an area where there's enormous gravity near a black hole, so time was much slower to them than it was to people outside of that black hole, distant from that black hole, where they weren't affected by gravity as much, and therefore their time scale went faster than the people's time scale that were near the black hole. And when they got back, what was for them just a couple hours turned out to be 20 years or many years for whoever was waiting for them. And this is a real thing, but we haven't done it to that extent. So this sort of field distortion, I mean, other types of fields, we're not talking about distortions like the gravitational field, but there are other fields like magnetic field and electric field, which we'll talk about in later units. So fields are represented by field lines, and this is going to be true for all the fields that we talk about: gravitational field, electric field, magnetic field. The field lines for gravity are always pointing towards the center of the object. Why? Because gravity is only an attractive force. It pulls things towards the center of its mass, in this case, the Earth. So the inward direction of the arrows indicates it's always an attractive force. Electric force can be repulsive or attractive. If you have like charges, they repel. So the force lines will be pushing against one another. If you have opposite charges, they will attract. One will be putting out force lines, and the other will accept force lines, and that will connect them. And the same thing with magnetic poles. The North and South Pole, North poles will repel each other. North and South Pole will attract each other. All right. So and this will be the same also for all types of fields. The tighter the field lines are, and the more lines you are drawing, that represents the fact that the field, the overall field, is stronger. So for an object that has a lot of mass and has a lot of gravity, you would write lots of these arrows pointing in towards the object. If it had weak gravity, you would just have a few lines pointing in. So the density of the lines, the crowding of the lines, is an indication of how strong the field is. So let's talk about something really bizarre. We're going to talk about the gravity not just outside of the Earth or any planet, but the gravity inside the planet, a solid object. And this is a little hard to conceive, but let's talk about outside the planet first. We can talk about it as if it's Earth, but it doesn't matter what object this is. Well, if you're on the surface of the Earth, you're one radius away from the center, right? The R value. That's your distance. That is your D that we would square in the formula. And the formula works great outside of the Earth. Kind of falls apart when you're on the inside of the Earth, okay? You can't use that gravitational formula that I showed you before of big G m1 m2 divided by d squared. Outside of the Earth, it's fine. Outside of the Earth, when you're on the surface of the Earth, your distance is the radius of the Earth, which works out to be about 4,000 miles. We're always 4,000 miles from the center of the Earth, okay? And as you go further, the force of gravity will decrease with the inverse square law. We already saw that. We can mathematically figure out how the force decreases as the distance increases to the square of the distance. That's pretty straightforward, and this is the inverse square law that we've been talking about. All right, but the reason why this works is when you're on the surface of the Earth or you're leaving the Earth completely, all of the mass of the Earth is quote unquote below you. It's under your feet. What if you're inside the Earth? Well, now inside the Earth, and I put a little red dot to show inside the Earth here. If you're inside the Earth, some of the mass is below you, some of the mass is on the other side of the Earth, but some of the mass is above you if you went down into the Earth. And as a result of that, there's less mass creating gravity. And where that gravity, that center of gravity is coming from is also a little different because if you're breaking it up into the Earth that's above you and the Earth that's below you, it becomes a calculated calculus formula, okay? But suffice it to say, the result is fairly simple. The deeper you go, gravity will go down linearly on the inside of the Earth until you hit the center of the Earth, in which case the center of the Earth has absolutely zero gravity because your distance to the center of the Earth is zero. And therefore, there's no gravity at all in that case. So no matter how heavy you are technically without any weight at all in the center of the Earth. There is zero gravity in the center of the Earth. And this is true for a solid body. If you were in a hollow Earth, anywhere in the hollow would be zero gravity because that's also a weird calculus formula you don't need to know either. I just threw that in. But if you're inside a body, it decreases linearly down to zero. If you're outside of the Earth, it never gets to zero. It can go on and get smaller and smaller, almost zero, but never actually zero. So here's a weird thought experiment here. Suppose you have a hole that cuts all the way through the Earth. From one side of the Earth to the other, there's a hole that you can jump in. And let's make believe it's not boiling hot by the center of it and that you would fry. Let's make believe you can safely travel through. There's no air resistance, and you can just go through the center of the Earth. Well, when you're at the top of the hole, about to jump in, you've got maximum acceleration. That's the full G of acceleration, 10 meters per second squared. And what happens is you have no velocity initially. You're jumping with zero speed. You jump down in the hole. Your speed will increase and increase and increase, but as you go lower and lower, there's less mass underneath you, and therefore you'll feel less of a gravitational pull. And your gravity, the acceleration due to gravity will actually decrease linearly as you go in. So if you get halfway to the center, not halfway through the Earth, halfway to the center, so we're a quarter way through the tube, gravity is half at that point. So you're still accelerating because you have acceleration. You're still going faster and faster. You're not accelerating as quickly as you were before, but you're still getting faster and faster. So by the time you get to the center of the Earth, you're at the maximum you're ever going to get. But now the gravity is zero. But you're flying so fast through the Earth that even though you have nothing pulling you, your momentum will pull you right past that point. And past the center, you're going to start feeling gravity again, but the gravity's pulling up the other way, pulling towards the center, and you're going away from the center to come down to what looks like the bottom in this picture. So the acceleration is going to be increasing in the wrong direction. You're going to get slower and slower until you end up coming to the mouth of the other end of the hole, but your velocity will end up being zero by the time you reach the end of the hole, and your acceleration in the opposite direction will be maximum negative, pointing the wrong direction of your travel. So hopefully you can grab onto the ground as soon as you get to the top so that you don't fall back into the hole, because otherwise you'd be zigzagging back and forth pretty much forever. Now, somebody did a calculation on this and figured how long would it take, given what we know about gravity and the changes in the acceleration due to gravity as you go through the Earth, and the fact that it'll be zero in the center, and then it'll be fighting against you as you're coming down the bottom end of this tube to the other side of the Earth. They figured, what if you could do this and there was no air resistance stopping you? It works out to about just under 40 minutes to go through the Earth from one side to the other. That is an enormous improvement over flying halfway around the world. But that's because you're going to be moving at such incredible velocities by the time you're at the center of the Earth. That's what allows you to go all the way through, because gravity just keeps adding to your speed as you're falling down, but then when you're coming out, it'll slow you down until you get back to zero when you come out the other end of the hole. All right, so let's talk a little bit about Einstein's theory of gravitation. So Einstein said that gravitation is actually a warping of space-time by any object with a mass. So that could be a star, a planet, a moon, you, me, a truck, an ant, a proton, anything. The more mass of the object, the bigger dent in this space-time fabric, the fabric of the universe. And the way people think about this is because we can't think about 3 dimensions very easily, and distorting 4 dimensions. We can think about distorting 2 dimensions. If you had a big rubber sheet and think of that as your space-time, you can think of space as 1 dimension, even though it's 3, and you can think of time as the other dimension, and that's 1 dimension, right? And just drop something massive on a rubber sheet. Well, that sheet is going to curve down, and it's going to curve down more. It's going to be more and more distorted depending on how heavy an object you drop on the sheet. And the way it mimics gravity is that when people have done this and dropping some object on a rubber sheet, and then they'll take a small object like a little ball and they'll give it a little velocity, you'll actually see it spinning around the big object that's sitting down in this gravity well. That's what it's called, gravity well, because of the shape, the distorted shape of space-time. And this is a kind of a halfway vision of the distortion of a 4-dimensional space-time, but it allows you to kind of vision with the human brain what's actually happening, the way Einstein sees what's happening with gravitational fields warping space-time. So the bigger the ball, the greater the warp in the fabric, and every object with any mass will form its own distortion. So you can put different balls in different places, and you know that if you put a really heavy ball in the middle and you gave another ball no speed at all, no velocity at all initially, and just let it sit, it'll probably eventually roll down into the big ball. That's the gravity pulling the two balls together. So a warped space-time affects the motion of all objects with mass, everything, anything with mass, proton, all the way up to a super giant star, okay? And you can mimic this with marbles and bowling balls on rubber sheets or water beds if you actually have that, but be careful, it's easy to destroy those. All right, so black holes. You've undoubtedly heard of a black hole, maybe you know what it is. So a black hole is when a star shrinks. Usually this happens when stars are in the ballpark of more than 8 masses, 8 times heavier than the mass of our sun. Our sun's not big enough to turn into a black hole, but bigger stars have enough mass that eventually, when they stop burning all the fuel, when they stop doing all the fusion that generates heat and energy, pushing the body of the star out, when that runs out, the gravity force is unimpeded and will just pull the mass in. And if it pulls it in to a certain extent, it will become what we call a neutron star, which we're not going to talk about here. But if it pulls it in even further, eventually it becomes so small and so compact that the gravity near the surface of that object is so high that nothing can escape it, including light. Light doesn't have enough speed to get out of the gravity of the star, of this black hole star. And you might say, well, wait a minute, light doesn't have any mass, but there is an equivalency between energy and mass. So when you do that, you find that light is distorted by heavy gravity. And we know that for a fact. This is not just supposition, it's not just theory. We've actually demonstrated it. In fact, there are pictures from the James Webb telescope that just came out a week or so ago that show the distortion of light coming from very, very distant galaxies that are 13 billion light years away. And we can actually see the same galaxy multiple times because light was distorted in such a way that multiple images of the same galaxy came to us in one photograph. So it's pretty remarkable. But anyway, so a black hole is when a star collapses on itself, and we're going to make believe that no mass is lost. We actually do lose mass, but we're going to make believe no mass is lost when it collapses into a black hole. But all the mass is there. For the most part, we're going to assume all the mass is there. But it just has a smaller radius. In other words, when you're standing on it, the distance between you and the center of the black hole will be much smaller than if you were able to stand on the surface of a star. Obviously, you can't do either one. Both would kill you, kill anybody. It would crush you or burn you or whatever if, in the case of a large star. So if you were on a big star and for some reason the gravity pulled it in and it became half the radius. Well, half the radius means a much smaller star, and half the radius, because of the inverse square law, cutting the radius by 2 means we're increasing the gravity by 4, the force of gravity by 4. It's an inverse square. So the gravitational force is based on the familiar formula, the gravitational formula, the universal gravitational formula here, but we're changing d. We're not changing either mass. The masses are the same. We're just making d shorter. And if we cut d in half, we will increase the gravity force, the F sub gravity, by 4-fold, 2 squared. So black holes. Black holes form when the stars collapse under their own gravity because they don't have enough heat energy, thermonuclear energy, pushing them out. When it burns up enough fuel, it just can't stop itself from collapsing. And it will become so small that the gravitational force on the surface is insanely high. So high that, like I said, light won't escape. Nothing can escape. And that point, that distance from the black hole where even light can't escape, is called the event horizon, if you've ever heard that term. So anything in the vicinity of the black hole is going to be attracted by the black hole's massive warping of space-time, just massively warped. You can see this thing is pulling space-time down in this giant warp. So anything nearby will fall into this gravity well and be pulled towards the black hole and swallowed up. And we don't know exactly what happens once an object is inside the event horizon of the black hole. There's a lot of debate about it, but it certainly should be destroyed. I mean, there's some talk, there might be some things, sci-fi things that people would like to think about. And one of those is white holes, which we'll talk about in a second. All right, what would happen if to the Earth if the sun's mass collapsed upon itself to form a black hole? It would break away from the attraction of the sun. It would be pulled into the sun. It would become a black hole too. None of the above. Think about that. So we're collapsing the sun into a black hole. So what is that doing? That is just making the sun smaller. Is the center of the sun the same distance to the center of the Earth? Yes, it's exactly the same distance when we collapse the sun. Watch the sun here. Still the same center. So the distance has not changed at all. Has the mass of either the Earth or the sun changed when we collapse it? No. So the gravitational force will be absolutely identical on the Earth. The Earth's force on the sun and the sun's force on the Earth will be identical to what it was before. It will be the same all the way through. Nothing changed because the formula only includes masses and distances between centers. Now, if you are on the surface of the sun and the sun got smaller, so you're now on a surface that's closer to the center, that's different. But if you're talking about a star collapsing and you're over here, your distance to the center of that is not changing at all. And therefore, nothing in this formula changes. You'll feel exactly the same gravity. So the Earth will keep rotating around the sun just as it always was. The problem is, while there's no change in gravitational force, we would stop getting sunlight and heat and anything else coming from the sun in about 8 minutes and 20 seconds, because that's how long it takes sunlight to reach us. In fact, when we're looking at the sun at any moment in time, we're never looking at the sun right now. We are always looking at what the sun looked like 8 minutes and 20 seconds ago, because that's how long it took that light to reach our eyes. Wormholes. Now, wormholes are totally theoretical. People have thought about them, people have looked for them, but nobody's found them. This is the stuff of sci-fi, but it might be reality at some point in the future. So it's another enormous distortion of space-time fabric, but unlike a black hole, it doesn't just go down to the black hole and end there. It might, in theory, end up spreading out at some other part of the universe, in another location entirely, or even in a different universe. So this is what's discussed. And we've never found one. They're completely theoretical. Okay, so universal gravitation. It affects everything. Everything affects everything else. Anything with mass and even light are affected by gravity. Okay? The Earth is round because of its own gravity. It's the fact that the Earth has all this mass pulling in on itself and forming a ball. And in fact, all the planets and all the minor planets, what we call dwarf planets, and the moons that are round, they're round because their own gravity was big enough to pull the stuff they're made of equally in all directions to make a sphere. That's why planets are round. Same thing with stars, for the same exact reason. The universe is expanding. We know this. We've known this for quite a while. But what's interesting is the rate of expansion of is actually accelerating. It's getting faster and faster and faster over time. We don't completely understand this, and this is in part due to something we call dark energy and also to dark matter, which are both theoretical concepts. They're kind of placeholder names until we really know what they are. So it's extremely complex, and I don't pretend to understand all the details of it either. But the universe is expanding. So gravity is not going to eventually pull us all back in together. It's going to keep going out and expand. And with that, we'll end here. Thank you very much.